Neutrons are the neutral particles bound inside the atomic nucleus. We all agree about that, but do you know they can come out of the nucleus, ejected by a decay process or by a nuclear reaction? Okay, follow this lecture. Here we'll present a quick overview of neutron sources and a short introduction to neutron detection. Let's start with an experimental evidence. Neutrons, the tiny particles that constitute the atomic nuclei, can often be found free in nature. Not only that, being neutral, they move through matter very easily, randomly interacting with atomic nuclei through very different nuclear reactions. Depending on their kinetic energy, neutrons can trigger nuclear transmutations, can collide like billiard balls, or can be captured. But where do free neutrons come from? The answer to this question is not unique, because many different processes lead to the emission of neutrons. Spontaneous fission, isotopic sources, nuclear fission, accelerator-based reactions, and many others. Let's consider as useful examples just two of them: spontaneous fission and isotopic sources. Spontaneous fission is a decay process that produces, let's say directly, neutrons. As indicated by green regions in the table of nuclides, the spontaneous fission is typical of some heavy nuclei as an alternative to other processes. In a spontaneous fission, an unstable nucleus splits into two lighter nuclei. The products are always highly unstable and eject sooner or later one or more neutrons. The leader of this category is californium-252, the most widely used neutron source from spontaneous fission. Anyway, this is just an example, but it's practically very important to bear in mind that many heavy nuclei, such as isotopes of uranium and plutonium, have always a low but not null probability of undergoing spontaneous fission. In all cases, the typical kinetic energies of fission neutrons range between tens of keV up to about 10 MeV. Another way of producing neutrons is to mix alpha and gamma emitters with target nuclei having high cross-sections for alpha N or gamma N reactions. In such a coupling, target nuclei react with an alpha or a gamma particles and free neutrons. The typical target nucleus is beryllium, a material that maximizes cross-sections and consequently the neutron yield. A good example of isotopic source is the americium beryllium, an alpha N source assumed as a reference in the ISO standards. Other examples are plutonium beryllium, polonium beryllium, radium beryllium, curium beryllium, and americium boron. Kinetic energies of neutrons produced by isotopic sources go from tens of keV up to about 10 MeV. Okay, so far we've had a look at some ways of emitting neutrons. Now, what happens to free neutrons? Well, they start interacting with matter via different nuclear reactions, dissipating their kinetic energy. Being neutral particles, neutrons tend to collide with nuclei by undergoing the so-called scattering interactions. This is especially true when neutrons move within low atomic number materials, where the energy dissipation due to collisions results to be very effective. The slowing down process, called moderation, ends when neutrons reach the minimum kinetic energy possible, the thermal energy. In real situations, the final effect of such a behavior is the coexistence in the neutron field of all kinetic energy components, from the maximum emission value down to the thermal one. For this reason, neutrons up to 20 MeV are conventionally classified according to their kinetic energies. We have thermal neutrons characterized by energy values ranging from 0 to 0.5 eV, epithermal neutrons with energy between 0.5 eV and 100 keV, and fast neutrons with energies higher than 100 keV up to 20 MeV. Each class has its own physical features and processes that are exploited also to detect and measure the neutron field. Let's give you some elements about that. First of all, a simple consideration. In order to detect and measure neutrons properly, we need to exploit the phenomenon with a good probability of occurrence. In other words, we have to set up experimental conditions able to promote neutron interactions with high cross-sections. Moreover, we must do so by exploiting interactions whose effects are clearly detectable. Well, the experimental evidence shows that these conditions are met by some neutron capture reactions at thermal energies. More specifically, we nowadays know that at thermal energies the nuclei boron-10 and lithium-6 have a high cross-section for N-alpha reactions, while the nucleus helium-3 has a high cross-section for the N-p reaction. This is the reason why thermal neutron detectors are instruments that exploit typically materials containing boron-10, lithium-6 or helium-3. An important example is given by helium-3 gas detectors. These are cylindrical or spherical chambers filled with helium gas enriched with helium-3. By means of electrodes, a proper electric field is set within the chamber. So, when the thermal neutron enters the chamber, it is likely to react with the helium-3 nucleus of the gas. The reaction produces a proton and a tritium nucleus at a given kinetic energy. Once emitted, the two products release their kinetic energy in the gas. The result is the ionization of the gas with a consequent generation of a certain amount of charge. The charge is finally collected by the electric field to create an electric signal that can be counted. This is the thermal neutron counter, and let me say, one of the best. And what about neutrons of energies higher than thermal? How can we detect epithermal or fast neutrons? The correct answer is with many different methods. However, one of those is based on the use of the thermal neutron counters that we just mentioned. This method exploits the moderation of fast or epithermal neutrons in low atomic number materials such as plastics. Therefore, by properly combining layers of plastic and thermal neutron counters, it is possible to perform a detection of the different neutron classes. So, to wrap up, we talked about neutrons, how they are produced, how they can be classified, and how they can be detected. Each one of these aspects results to be strongly related to the physics of nuclear processes, physics that can be exploited to manage neutron fields.